let me begin by thanking the organizers for including me. It's my first time in Australia, so I was happy to be here. So today I'll be talking about some recent work that I've done with two of my PhD students, Yifan and Jingkang. I'd like to, in particular, acknowledge Yifan for sort of sparking my interest in LDPC codes, which will become the sort of star of the talk. And then I also sort of acknowledge the military-industrial complex for supporting this work. So, I'm going to tell a story that I hope is sort of very simple for a very long time, and then I will try to argue that the leap to the sort of more exotic LDPC codes is mathematically very simple from the perspectives I'll take in this talk, but that it has very sort of surprising physics implications. So this is going to be a kind of physics maybe view on codes. But yeah, OK, let's start off very simple. So the goal of error correction is to protect logical bits by encoding them in some kind of redundant fashion among physical bits. The simplest example of this would be the repetition code. I'm certain this must have been invented like hundreds of times in history, right? Because it's a very simple idea that you just say the same thing over and over and over again, and someone is probably more likely to understand you if you say something 50 times than if you say it once. Okay. So anyway, if we have a single logical bit, 0 or 1, we can say the same thing many times. And even if sometimes we accidentally say the wrong thing, probably more likely than not, you'll be able to understand it. In this problem, I'll be talking about, for the moment, we'll focus on classical codes. If I have n physical bits, I'm encoding k equals 1 logical bit, right, among the n physical bits. Just to review the jargon here, the smallest logical operation I can perform on my code words is to flip all of them. So I therefore define something called the code distance d to be sort of the number of those bit flips. And of course, it's n in this problem. Now, the repetition code is an example of a more general family of codes called low-density parity check codes. It's maybe not the prototypical LDPC code, but it does mathematically sort of check all the right boxes. So what are the boxes that we're trying to check here? So a parity check code is going to correspond to essentially a matrix with 0 and 1 entries, which I'm calling H here. If I do my matrix vector multiplication, mod 2, then I can say that the code words of my parity check code are the right null vectors of this matrix H. So why does this matrix encode the repetition code? Well, if I multiply H times X, the first row sort of gives me the condition that x1 plus x2 equals 0. And mod 2, that means x1 equals x2. We keep on going through all the rows, and we deduce that all of our bits should be the same. And these are indeed the two logicals of the two different logical code words of the repetition code. It's low density because each row and each column of this matrix H are sparse. Okay? So none of the parity checks would involve sort of looking at some finite fraction of a large n number of physical bits. So in some sense, we can kind of locally, or maybe k-locally, check whether any tentative code word is an actual code word. Now, from a physics perspective, we could say that once we have this repetition code, we could think of the sort of logical code words as ground states of a certain Hamiltonian. This Hamiltonian can be written maybe in a sort of more pretentious way like this. Absolute value bars here denote the number of ones in my vector, or the Hamming distance. So this mod of H times X just counts essentially how many parity checks are violated. But if I do a little bit of relabeling here, and I work with, let's say, capital Z is 1 minus 2x, then this Hamiltonian is just the 1D Ising model. Okay? So in some sense, the physics of this particular LDPC code ought to be captured by this Ising model. Okay, so kind of now turning to maybe a physics perspective on the decoding problem. So how would we decode this repetition code? The simplest thing we might do is to do a kind of majority vote. So we look at all the bits. If more of them are 0 than 1, then we'll guess that you were trying to send the message 0. Okay. But this is sort of, while maybe mathematically it's very likely to succeed at low error rate, it's sort of awkward in other ways. For example, this is a global decoder, right? We need to look at the whole system. And also, if we're sort of making mistakes, if there are bit flips occurring at constant rate, we would need to keep checking, right, over and over again to sort of reset our majority vote. And this might be a little bit expensive. You know, think of like you have a phone, you have pictures on it. It would be like you always need to be like plugging your phone into a power outlet to make sure that you're never losing information. The dream would be that you can unplug your phone, you can unplug your computer, and you don't lose your information. Okay? So I have information I'm trying to store on my laptop. Okay, I can throw it into liquid helium, which is cold, by keeping the system at low temperature. Therefore, I can protect my information. Okay? So the dream is to basically, rather than needing this kind of active decoding, I would say we should aim for a kind of passive decoder where you just put the system in contact with a heat bath and it will correct itself. Okay. So a little bit more on these passive decoders. So I would say that the first two criteria that I'm going to demand are maybe the more important ones. These are kind of physical criteria. So firstly, I want a passive decoder that is memoryless. Okay? I don't want to have to know the whole history of, like, don't tell me your life story. I just want to look at the current state of the system and be able to sort of deduce what I should do next. But I also want my decoder to be local. I want it to only require sort of a handful of bits worth of information to deduce whether to make a move or not. Okay? A formal definition you might ask for a decoder to be passive is that it is time reversal symmetric, or if you prefer, it obeys a detailed balance condition. Okay. The goal of the passive decoder is not to sort of hand you a code word that is an actual code word. I can have a finite density of errors in my system, but I just need to make sure that whatever density of errors I have, that I'm not sort of straying all that far from a code word. Okay? So as long as I'm kind of close enough, then I'll say that the passive decoder is working. And we'll see what that means very soon. Okay, so with these ideas in mind, I would say the kind of physics-inspired passive decoder would be something called a Gibbs sampler. The role of the Gibbs sampler, the goal, is to drive the system to thermal equilibrium. Okay? So I want to say that after running the Gibbs sampler for a long time, the probability that I see the system in any microstate x is proportional to e to the minus beta h, where the curly h was my Hamiltonian from before that counted the number of violated parity checks. Okay? And what I think is sort of amazing is that there are really simple microscopic rules that are guaranteed to drive you to this configuration. So using sort of only single bit flips at a time, okay, we can essentially take a classical system and drive it to this Gibbs state. The way we do this is like this. So at each time step, I'm going to sort of pick a random bit out of a hat. Then I ask, do I want to flip this bit? If flipping the bit would lower the energy, I'll always do it. Okay? But if flipping the bit would raise the energy, sometimes I'll do it anyway. Okay? Like I just dump my own errors into the system with some probability. And if I do this with a very specific probability, then it turns out that the late time probability distribution will be thermal. Okay? So this Gibbs sampler you can think of as a kind of cartoon for the actual thermalization dynamics of our system with the heat bath that we've dunked it in, or cold bath that we've dunked it in. Okay. So the problem with this Gibbs sampler, right, is that for our kind of simple 1D Ising model that we've been discussing, it will not work, okay? And why won't it work? Well, let's say I have sort of this segment of my repetition code, and I have 3 errors on the left. Okay, locally the Gibbs sampler will go and look at all of the parity checks, right? And the only violated parity check is the one at the boundary. Now, I don't know if I'm a local Gibbs sampler, right, whether I should, flip this one or this one, okay? And so this domain wall is going to diffuse through the system, and the memory time will basically be polynomial in system size, okay? And that's even with, if you only flip 1 bit at a time. If you're flipping finite density at a time, you'll fail in constant time, okay? Now, from a physics perspective, we kind of know exactly how we should fix this problem. The sort of, the repetition, yeah?
Sorry, when you're saying that Gibbs sampling fails, you mean it fails to decode the information you put in there?
Protect information. Yeah. It will thermalize. It thermalizes quickly.
Yeah.
But that's sort of, it's not good in this setting, right? So we sort of want the Gibbs sampler to try to reach thermal equilibrium but fail, because there are 2 code words that are equally likely in the thermal state, but we only want to see one of them. So we actually want the Gibbs sampler, so maybe fail here is misleading. We want it to be slow, okay, and it's not slow in 1D, right? Now, from a physics perspective, we can maybe state this mathematical observation in the following way. There are no phase transitions in the 1D Ising model, because creating a single domain wall, right, you can freely proliferate that domain wall, and so the entropy of where to put that domain wall always wins. But we know that in higher dimensions, there is an honest phase transition in an Ising model, okay? So therefore, if we sort of take the same repetition code with the same code words, but we instead think of the code Hamiltonian as sort of a 2D Ising model, like we look at parity checks, both in this form, but also maybe in some kind of long-range way if we kind of snaked around, 1D. Then we would expect to see an actual transition, okay? And this is good because now, we can have our floppy disk. We can store information in that device and just leave it on a table at room temperature, and it won't degrade, okay? So having the kind of passive classical memory is actually quite important for modern life. Okay, so to dive back into the sort of formalism, why is this happening? So why do we have robust information in 2 dimensions from a dynamical perspective? Well, the reason is that if I now look at my error cluster in the 2D Ising model, I notice that, for one, there are far more flipped parity checks, okay? But more importantly, these flipped parity checks kind of measure the boundary of a domain. And in 2 dimensions, right, we know that we can't have a large domain with an order 1 boundary, okay? At least until we get way past half the system size, in which case we've introduced an error. So the idea is going to be that we can essentially constrain how likely it is to see a kind of big domain wall, okay? So in the Gibbs ensemble, let's estimate what's the probability that a given bond, let's say, is involved in a length L domain wall. If L becomes of order the sort of length of the 2D lattice, then we worry we could introduce logical errors. But if L is very small compared to the lattice size, then we're not worried, okay? We'll have like lots of little clusters, but they're all decodable. And they're independently decoded. So the probability that we have a long domain wall, there's an entropic factor, like I have some walker moving on the lattice. Where do I go? That's this 3 to the L. But for every domain wall of length L, there's an energy penalty, right, of 2L. So I have this kind of Gibbs suppression factor. And this probability, of course, becomes negligible at large L as soon as beta is larger than log 3 over 2. And this is actually not so far off from the honest critical temperature of the 2D Ising model, okay? So the punchline is that in this redundant code, we get these kind of domain walls that form. And the existence of these domain walls sort of makes Gibbs sampling slow. The fact that you have to pass through this very unlikely configuration with a long domain wall, okay? Any questions before we continue? Okay. Hopefully so far pretty simple. Okay. In general in this talk, I'm going to maybe be a bit glib about the classical to quantum transition. But for the purposes of this talk, moving from a classical to a quantum code is never really going to introduce a sort of serious subtlety. Okay? It's just kind of a more annoying bookkeeping. Okay? Again, it's a bit glib, but okay. A quantum LDPC code for us will be essentially a pair of classical LDPC codes that obey a kind of particular constraint on the two parity check matrices. And the purpose of this constraint is to ensure that the x-type and z-type stabilizers all commute with each other. Okay? And so if I have this pair hx and hz, I can form a quantum CSS code. I can define a Hamiltonian the same way that I had before by just summing over all of the stabilizers that I'm given. Okay? The simplest example of one of these codes that in the thermodynamic limit has a large distance is going to be our kind of quantum analog of the 1D Ising model, which is called the surface code, or the 2D surface code. Like the 1D Ising model, right, we're going to have sort of logical operators that look like big strings, except that we need two logicals, an x and a z, and so we have a sort of horizontal and a vertical string. So 1 plus 1 is 2 dimensions. It's all consistent. The parity checks of this code, right, form this kind of nice lattice structure. Okay. Like the 1D Ising model, this cannot be decoded passively. Okay? The mechanism by which passive decoding fails is exactly the same one that we saw for the 1D Ising model. If I start introducing errors on one of my logical operators, then my local sort of passive decoder, well, everywhere here, it's totally happy. There's no violated parity check. But then I see there's a single violated parity check in this plaquette. And I don't know whether I should sort of start applying my own errors moving to the left or to the right. Okay? And so the sort of endpoint of this error string freely diffuses. This is really a general problem with two-dimensional stabilizer codes. Okay, so yeah, in particular, there's no topological order. I think that's defined in like a slide or something at finite temperature, and so we don't expect any kind of passive decoder to be sensible in this setting. That's not to say that you can't do decoding on this code, right? But you again need to do something that's kind of active, and it's often global, like minimum weight perfect matching. You're really looking for like which two anyons, which two endpoints of these error strings are closest together, and I'll try to annihilate them. It's doable, but again, this is like plugging your iPhone into the power outlet just to not lose your photos. You don't even want to do anything, but just to maintain information, you're kind of expending energy. Okay. All right. Now, if we want a sort of passively decodable quantum code, okay, thank you. All right, the next, the simplest one is in 4 dimensions, okay? And it's sort of 4 because 2 plus 2 is 4. We need 2 dimensions to correct x errors passively and 2 other dimensions to correct z errors passively. Like the meme says, I can't draw things in 4 dimensions, but just trust me that this works, okay? Now, like in the 2D Ising model, there is a thermodynamic phase transition in the 4D toric code. Okay? So when you cool the system below some critical temperature, you find a non-analyticity in the free energy. Sorry, yeah, it's fine. Okay. What does this non-analyticity correspond to? It corresponds to the fact that at high temperature, the thermal state is sort of easy to prepare or to approximate. It's very close to a product state. Whereas at low temperature, the state becomes topologically ordered. Okay? It's not possible to prepare this state with a finite depth circuit. Okay? And moreover, just like in the 2D Ising model, if we ask what's the probability that in this low temperature ensemble, we find a state that has kind of half of a logical operation, so it's a non-decodable error, that probability is exponentially suppressed. For exactly the same reason that it was in the 2D Ising model, we have this big domain wall of violated parity checks. Okay. So, all right, that means it's easy. We can sort of build our analog of a quantum floppy disk. We just need to build the sort of 4-dimensional toric code. Okay? And then we realize that we don't live in 4 dimensions. Okay? And so, can we do this in our real world? Okay. There was a lot of work, kind of, maybe I can even say before my time, although I'm getting kind of old, but I think right when I was starting grad school, there was a huge amount of work on trying to look for low-dimensional quantum memories. And I think the best example that I'm aware of is something called Haas code, which is not a quantum memory. Okay? It does have a finite lifetime. It may be long, but it's finite. And again, being kind of a pedantic theoretical physicist, I really want something whose lifetime is infinite in the thermodynamic limit. Okay? And I don't know of any example like that. There's a good reason for this. So for these spatially local codes in particular, in 3 dimensions, you'll have a sort of membrane-like logical operator, which is robust, but then you have a string-like logical, which is not. Okay? So we really needed to go to 4 to have 2 membranes. Okay. Now, all right, if we want a quantum memory, as far as I can tell, we probably just need to abandon spatial locality. So then, why stop at 4 dimensions? Like the 4D toric code only gives us 1 logical qubit, but we've got to do something crazy in our hardware. So why not go all the way up to something infinite dimensional and see what we can get? Okay. So in that spirit, let me now kind of state, and with the history that I've told you in mind, let me now state the punchline of the talk. So firstly, when we look at a kind of random family of LDPC codes, we'll see that these random LDPC codes are sort of completely boring thermodynamically. So they're like the 1D Ising model, actually in a very precise sense. And this is going to be true for both classical and quantum codes. At the same time, these boring thermodynamic systems can be passively decoded. So below some critical temperature, the Gibbs sampler will have an exponential mixing time. Okay? So you can just throw your system into a heat bath. You don't need to plug it into the power outlet, and it will decode itself. Okay? So I think already, from a physics perspective, that's kind of cool. So there's a complete sort of break between 2 things that had before seemed quite closely linked in coding. Basically, the existence of a thermodynamic phase transition and the existence of passive memory, okay? Or of classical and quantum memory and passive decoding. These are not, these can in principle be sort of orthogonal aspects of a problem. So obviously there's this sort of deep contrast between what we've seen for like Ising models and toric codes, but I'll also argue that this is sort of unusual from the StatMech perspective, and that this is, these models will become a kind of glass that has no frustration in it, okay? And of course, this frustration-free glass also is sort of invisible to thermodynamics, okay? And I think this is very unusual. This is a purely dynamical phenomenon that I don't know how to sort of visualize or to essentially calculate in a sort of non-dynamical way. Okay? And at the end of the talk, I'll also argue, although this is kind of, I would say, a preliminary idea, that these LDPC quantum memories have a lot of kind of appealing features for, in particular, the neutral atom platform. So I'm not going to say that this is like the way one should build quantum computers, but I think there is a reasonable shot that in the not too far future, we could at least realize a kind of prototype quantum memory in this platform. Maybe that will get you a flashy paper and never do anything beyond that, but that's still good enough. Okay. Okay, maybe any questions at this point before I continue?
Actually, could you say precisely what you mean by thermodynamically trivial?
Yeah, so the free energy is a smooth function. So there's no, you cannot measure anything thermodynamic and detect a transition. I'll sort of emphasize this again shortly. Yeah.
Thank you.
Okay. All right, so again, we're going to sort of spend more time on the classical problem. The quantum problem will have a few extra bells and whistles, but it will all kind of be analogous. So, okay, we're going to now study a different kind of low-density parity check code, which I've heard of as sort of delta B comma delta C. These are essentially going to be randomly constructed LDPC codes, subject to the constraint, the following constraints on this matrix H. So first, we demand that every row of this matrix H has exactly delta C ones in it. Okay? This tells us that each parity check has delta C bits. Okay? So this is kind of like a k-local problem or delta C local problem. In addition, we don't want any individual bit to be involved in a lot of parity checks. We don't want some kind of like highly clustered graph. We want something pretty regular. So we're going to just demand that each bit is itself involved in exactly delta B checks. This means that the columns of the parity check matrix are sparse, okay, and have delta B ones. Like the Ising model, there's a natural code Hamiltonian, which counts the number of flipped parity checks, up to these 2's and minus m's. M is just the number of parity checks in the problem. And if we convert this into our plus or minus 1 physics variables, our Hamiltonian is just the sum over all the stabilizers times the product of a z for each bit in that check. Okay? So it's not too much worse than the Ising model, right? Okay. Now this is frustration-free. This system has no frustration in that the ground states of this Hamiltonian not only minimize curly h, but they also minimize separately every single term in this sum. Okay? And lastly, of course, with our conventions, we always know one of the code words, which is the all-zero state. This is just useful for doing calculations because we know if we want to talk about dynamics near a code word, we'll just pick this one. Okay? All right. So now I want to go through some of the properties of these LDPC codes. At least some fraction of them are actually very simple to show, which really surprised me, but okay. The first thing we can actually very easily convince ourselves of is that this is what's called a constant rate code. So the number of logical bits in this system scales with the number of physical bits. And why is that? Well, by the rank nullity theorem, k divided by n has to be at least as large as 1 minus the number of rows of h divided by the number of columns. Okay? That's a bound on the number of right null vectors. Now, you can sort of convince yourself that with these constraints on bits and checks, this ratio m over n should be delta b over delta c. Okay? And we've taken delta c to be larger than delta b. I don't remember if I said that, but we're going to be doing that. So this ratio is always larger than 0. Okay? So these are constant rate codes. And with the sort of more annoying combinatorics calculation, you can show that this bound is almost surely saturated in the thermodynamic limit. In fact, depending on the values of delta B and delta C that you pick, you can actually say with probability 1 at large n, there is exactly no redundancy. So every single parity check in your random construction sort of kicks out one logical bit. Okay? All right, and now, if there are no redundant parity checks, we can show that this system is a boring thermodynamic system. And why is that? Let's do the sum in the partition function. So we sum over all states of e to the minus beta h. But I'm now going to do this sum in a kind of clever way. So rather than summing over x, I'm essentially going to sum in 2 steps. First, I'm going to observe that this condition, so if I like the syndrome equals h times x, because of this no redundancy condition, every possible s has at least one solution. There's at least one x for which this equation can be solved. And moreover, there are again, by the same idea, exactly 2 to the k solutions that basically differ by a logical code word. So we can do the sum over x as instead a sum over s multiplied by 2 to the k for that sum over code words. But now that we're summing over s, the Hamiltonian is trivial. It's just the number of ones in the vector s. And so we can just exactly evaluate this, and we essentially get the 1D Ising model partition function multiplied by the number of logical bits, exponentiated. Okay. So this immediately tells us that there are no thermodynamic phase transitions at finite temperature, right? Because the free energy density can just be calculated. It's a smooth function. So that's the thermodynamically trivial statement. Okay. Yeah.
So just wondering where the 2D Ising model contradicts this.
Right. So the 2D Ising model breaks this no redundancy condition. So in the 2D Ising model, if I look at the product of the 4 parity checks around a square plaquette, I get 1. So this is sort of a very simple argument that tells you that this redundancy is a necessary condition to have a phase transition. Okay. Yeah. Okay. The second crucial fact about these LDPC codes is that almost surely they have a property that's called linear confinement. What this means is that if I look at a state, let's say close to that 0 code word, where the number of physical errors is less than or equal to gamma times the number of bits, then I know that the number of violated parity checks will scale at least as fast as a proportionality constant times the number of errors themselves. Okay? So this is like a very strong constraint on how quickly energy barriers, like the sort of length of domain walls grows, if you will. Okay? Of course, this condition immediately tells us that the code distance is also of order n because, hx has 0 Hamming weight on a code word. So with this in mind, we can now prove very easily that the Gibbs sampler has an exponentially large mixing time. And OK, some of these steps may not be so familiar, but I assure you it's actually a beautifully simple idea. So the Gibbs sampler is a time reversal even Markov process. So the probability that in any time t, we go from, let's say, our code word to any other configuration is equal to the probability of going the other way times this relative sort of weight in the Gibbs ensemble, which is e to the minus beta times the number of violated parity checks up to a factor of 2. And of course, probabilities are bounded by 1, so this is just bounded by this exponential. Now, suppose that during the dynamics, we introduce a logical error. So we happen to stray very far from our code word x. So if that happens, then at least at one time t during the dynamics, we must have hit what I'll call the bottleneck set that sort of saturates this inequality. Okay? It's just impossible to have introduced a logical error until this happens. But we can bound the probability that we hit that set by just summing over all of these ridiculously crude bounds from before. That's bounded by the number of these states with gamma n errors times this Gibbs factor. But this is just bounded by 2 to the n, the total number of states in the system. Okay? And even if I do that, which is just crazy, right, I still get something that will exponentially be suppressed with system size once I'm below a critical temperature. And that's it. Okay? If the probability at any time is this small, I obviously have to wait for at least 1 over this time scale to introduce an error with any order 1 probability. Yeah?
Is that depending that you're doing the Gibbs sampling the first way you described it, like one local flip at a time?
So if you relax the 1 flip at a time, then actually, basically, okay, you can't move, as long as you move sort of much smaller than this distance, like maybe even gamma n over 6, if you moved that far at a time, this argument would still work. you would, because basically you would need to say, okay, well now the bottleneck is like all states with 5/6 gamma n to gamma n and so on. So it's a very robust argument. Yeah. Okay. Just as a kind of cute aside here, so my last semester in undergrad, I took a class on Markov chains. And anyway, I'm feeling very validated after all of these years that a lot of these mathematical methods that I learned in that class lead to very sort of simple arguments here. Okay. Anyway, so now we can kind of put together how the puzzle resolves itself. The Gibbs sampler is slow because we have very deep energy wells near all of our code words in the state space. So, I have this high dimensional space. I'm going to draw it in 1 dimension because remember, I can't draw things in 4 dimensions. And okay, so I have this landscape with 2 to the k different sort of basins for all the code words. These are very deep due to linear confinement. And so the Gibbs sampler gets stuck in one of them near our starting code word for this exponentially long time. Okay, and we just rattle around, introducing a very low density of errors. Okay, and that's easy to decode. Then the thermodynamics sort of sees this whole landscape. But it not only sees all of these other kind of code word basins, but it sees a whole sort of swamp of very sick configurations where, for example, I flip a single parity check. Remember that all possible syndromes corresponded to a physical state. And so I have to worry about configurations, all n of them that have a single flipped parity check. And there's n times however many logical states that I have, or maybe m. You get the idea. And there's then m choose 2 that have 2 flipped checks. So these overwhelm the sort of free energy. And that's why there's no phase transition. This is the only thing we're basically seeing at finite temperature. But dynamically, we're completely trapped near the code word. Okay? All right. Now, morally, I think this is very much like what you would expect to see in a spin glass. So in a spin glass, you also have this picture that when you enter the glassy phase, you get kind of trapped in some tiny part of the state space, and you just can't sort of escape these deep energy wells to see the full kind of complex energy landscape. But I'd like to argue that, at least in this setting, there's a few features of ordinary glasses that we're missing, which make this very interesting from a physics perspective. The first thing that an ordinary glass has is frustration. So, for example, if I look at something called the Sherrington-Kirkpatrick model, the Hamiltonian will be this kind of like random bond like Ising model, although all-to-all connected. These J's are random. And so about half of these terms in the ground state I can expect are positive and half are negative. So it's a highly frustrated system. In addition, we just had a very well-earned Nobel Prize a few years ago for the calculation of the free energy in this model and the demonstration that there's a spin glass phase transition. Okay? And it's detectable in the free energy in a replica symmetry breaking transition. We've also calculated the free energy exactly, and it doesn't have that effect. Okay? So, okay. I think the closest analog to this is the sort of NP-hard combinatorial problems. Here you could maybe argue that there are kind of glassy kinds of problems that appear frustration-free. So one example might be you're trying to sort of color a graph with 3 colors. Here there's a very sort of simple map, so it's possible to do this. But in the US, it's a little more complicated and you can't. Okay? So this is sort of an example of frustration that would arise in combinatorial problems. And yeah, what I would sort of say in this setting is that, at least in the examples that I know of, usually the kind of glassy, hard problem instances appear very close to a phase transition, maybe where you tune something like the density of bonds in the graph. And I don't sort of see the obvious analogy for the LDPC code. It really seems like the whole ensemble is frustration-free, and yet we have this kind of glassy physics. So I think it's very kind of exciting from the StatMech perspective. Okay. So again, we can now try to sort of race through the quantum analog of the story. The quantum story is very similar. The sort of only thing is that we need to find quantum LDPC codes to discuss. And this is a kind of frightening literature at times. We do have good quantum LDPC codes. The constructions are also kind of crazy, okay? And I haven't really understood any of them very well. I'm going to use a simpler construction, which is much easier to process, although maybe still a little subtle, which is called the hypergraph product code. This is going to give us a constant rate quantum LDPC code. So k will scale with the number of qubits, but the distance will only be square root n rather than n, okay? And the way that you make these hypergraph product codes has a sort of nice graphical picture. So you draw your classical code twice as what's called a Tanner graph. So we have circles for bits, squares for parity checks, and edges for which bit is in which check. We draw the graph twice, sort of one on the horizontal, one on the vertical. We use this kind of dictionary to convert the sort of doubled nodes in this square lattice into qubits or X or Z type stabilizers. And we put edges on rows and columns according to the classical Tanner graph. Okay? This, you can show, forms a quantum CSS code. It has, if the classical code has no redundancy, which we've seen is very generic, then we have this number of qubits, this number of logicals, and this quantum code distance. And I've just used sort of capital letters to emphasize this is now the quantum code, and lowercase for the classical code. Okay? Just like the classical codes, when the input is non-redundant, then the hypergraph product code is also non-redundant, and as a consequence, we have this kind of completely trivial partition function. And the proof is basically the same one that we gave for the classical system. We evaluate this trace in the right basis, where we enumerate the Hilbert space by the essentially eigenvalues of all the X stabilizers, the eigenvalues of the Z stabilizers. These are all non-redundant, so they're all giving us a new constraint. And then we have, of course, the logical information that's left. We count the number of X and Z type stabilizers. They can each be plus or minus 1. And we do this sum over the partition function and get the formula advertised. It's exactly the same, effectively, as the classical codes. So there's no thermal phase transition in the LDPC code. Now, let's talk a little bit about how we would do quantum Gibbs sampling. It's actually very close to the classical Gibbs sampler, but let's just sort of go through it quickly. So first, let me kind of describe, if I had a perfect quantum computer with no errors, we'll return to the error question shortly. But if I had no errors at all, I wanted to implement a Gibbs sampler, I would do it like this. So I just pick randomly, one qubit in the system. I measure, for example, all of the X-type stabilizers, the anti-commute with, let's say, Zi, or all the stabilizers that have Xi in them. And depending on how many outcomes I get that are plus 1 or minus 1, I will apply the following sort of gate to my state. Okay? And this probability is hopefully not too surprising. It looks a lot like this energy difference in our Hamiltonian. Okay? And you just do this over and over again. You pick different bits in different time steps. You can switch between X and Z. And this is basically what we mean by quantum Gibbs sampling. Of course, you could also try to parallelize this. So because the LDPC code is k-local, you can do this to sort of a finite fraction of the bits in every time step without sort of any awkwardness. OK. What I want to emphasize is that essentially the analysis of this Gibbs sampling dynamics basically reduces for this CSS code to a pair of classical Markov chains, okay? One for the X-type errors and one for the Z-type errors. And the only thing we need to be careful about is that the Hamiltonians for these classical Markov chains are hugely degenerate, not only because of all of the code words in the system, but because if we're looking at the X-type Hamiltonian, for example, every single Z-type stabilizer gives us another redundancy. And we just need to be careful about counting all of those states as well. I think the easiest way to do this is to use this notion of reduced error. So if we start with our code word 0, we essentially, given any kind of classical syndrome for just the X or Z type errors, we try to mod out essentially by all the stabilizers of the other type. Once you do that modding out, there's a notion of linear confinement that persists. Okay? So every error that, when reduced, has a certain sort of Hamming weight necessarily violates that sort of number of parity checks up to an order 1 factor. Okay? And with that ingredient, we can now again show that we have this, this kind of slow mixing time. So the Gibbs sampler gets trapped near one of our quantum code words for an exponentially long time. And the proof is very much analogous to the 2D Ising model that we mentioned before. So what we're worried about are configurations that look like this. They not only have some finite density of errors that we're going to, or flipped parity checks, that we should expect. This is finite temperature. But they have a very sort of dangerous, highly correlated cluster of, or highly connected cluster of errors. And if this cluster has sort of square root n bits in it, then we worry that that might introduce a logical error. So we need to basically say that the probability of seeing a cluster that's this close together is exponentially small. Okay? And that's indeed true because of this linear confinement property from before. We know that we have an e to the minus beta square root n sort of suppression factor from e to the minus beta h. But there's only a sort of another exponential number of ways to grow a cluster. So at large beta, we always win. Okay? And you can use a few other tricks, like Markov chain bottleneck theorems, to really prove that the Gibbs sampler gets frozen. Okay? Okay. So to recap, once again, we've seen that these hypergraph product codes are thermodynamically trivial, but they do have an ergodicity-breaking transition at finite temperature. Okay? So there's a kind of dynamical transition that's invisible to thermodynamics. Now, at this point, I'd like to make a sort of somewhat, well, strictly a conjectural, although I'm quite confident in, analogy to another recent story, which is the following. So if you take one of the actual good LDPC codes that has a constant code distance, it was shown that all of the low energy eigenstates of that Hamiltonian have a property called NLTS, which means that there are no low energy trivial states. That's the acronym. And trivial here means close to a product state. So this property means that every single eigenstate at low energy is topologically ordered. Okay? And this was proven a few years ago. Now, as far as I can tell, and we did ask some of these authors, it's not known actually how redundant these LDPC codes are. But it's probably the case that they're basically non-redundant. Okay. I didn't want to learn how that LDPC code works. It's quite complicated, so the hypergraph product was just simpler. Okay. But I'm almost certain that you could repeat the arguments we gave for this type of model, and then this would imply that there's a circuit complexity phase transition that's completely invisible to thermodynamics. And as far as I know, this would kind of be the first time that these two definitions of phases of matter are completely different. Okay. Yeah, this, okay. Anyway, I think this is really cool. Okay. So in the last part of the talk, I'd like to discuss a little bit about taking this kind of cute physics story that I've told you about the stat mech of LDPC codes and try to say, can we actually do something useful with it? This is kind of how I get funding. So, okay. Okay, so what I'm now going to argue is that having these kind of useful slow Gibbs samplers and quantum, passive decodable systems enables a kind of nice type of quantum error correction that's typically called measurement-free QEC. Okay? Now, the rules of the game for MFQEC are that I'm not allowed to do active sort of syndrome measurements, and I'm not allowed to do sort of feedback based on measurement outcomes. The only thing I can do is essentially unitary operations and this reset, where I just kind of force one of my qubits into the, let's say, the 0 state. Now, if you have a kind of memoryless decoder, you can always basically get to MFQEC from ordinary QEC. At least in principle. Here's a kind of simple diagram of how this works from this nice paper for a 3-qubit repetition code. So the first 3 rows in this circuit are my physical qubits. And the bottom 3 rows are going to be sort of ancilla qubits that I have to add for this MFQEC protocol. The first step essentially encodes each of my 3 ancillas with information about sort of which parity checks are violated. Okay? So for example, the first ancilla qubit is essentially measuring the parity check x1, x2. Okay? And once I've done that, this part of the circuit essentially corresponds to postulating that there's either 0 or 1 errors, and then looking for which of the parity checks were violated. Okay? And depending on which parity checks are violated, we apply a sort of logical correction operation to the physical qubits. It's basically identical to ordinary error correction, except the physical implementation is different. So mathematically, we're doing the same thing, but in experiment, this feels very different. Right? To make the sort of mathematical comment a little more clear, there's a formulation of measurement in quantum mechanics due to Steinspring, where you essentially use auxiliary qubits to store measurement outcomes. And then the measurement process and the feedback process become unitary. And we're basically trying to realize that physically in this error correction scheme. Okay? All right. So why is this sort of so useful now that we have, or when we have a sort of good passive decoder? Remember that we don't live in infinite dimensions, so we're not going to be able to just build an LDPC code, throw it into the liquid helium, and then pull it out, okay? Because we're not going to be able to wire, as far as I can tell, that kind of non-local connectivity at scale. Okay, so what are we going to do instead? Recall that the Gibbs sampler is k-local, so we only ever need to look at a few bits at a time to make a correction to any other bit in the system. And also, just as importantly, the Gibbs sampler introduces errors. Okay? So when we're at finite temperature, sometimes we deliberately put an error into the system, even if there aren't any. Okay? That was part of our sort of update rule for the Gibbs sampler. And combining these two things together, I now claim that we can build a useful, fault-tolerant, well, useful is in quotes, but at least in principle, we can build a kind of fault-tolerant, measurement-free quantum error correction based on these facts. The first bullet point is more of a useful thing. The fact that the Gibbs sampler is k-local means that the MFQEC circuit that we're drawing here is not having like n-qubit gates. Okay? So we only have order 1 qubit gates in the MFQEC circuit. That's really useful for an experimentalist. Okay? And that's coming from the fact that our Gibbs sampler doesn't need global information. We're just making local updates. Now, why is this fault tolerant? Well, it's fault tolerant essentially for the following very crude reason. So remember that we introduce errors into our Gibbs sampler at least this rate. Okay? So let's choose beta to be the critical beta, or maybe a little bit above it, to be safe. And if we could realize a Gibbs sampler at that low temperature, then we've already seen that it's a quantum memory. Okay? And so the gimmick is that we're just essentially going to say that our threshold for this circuit is essentially the one where the sort of global, the accumulated error rate during both the sort of idling time and the correction circuit, when that total error rate is equal to the sort of most unlikely move of the Gibbs sampler, then to build the perfect Gibbs sampler, we just add our own errors in all the other cases. Okay? And so that's, of course, probably crazy. I don't think you'd actually want to do that. But the point is that at least in principle, if you could realize the Gibbs sampling dynamics, you would necessarily have a quantum memory. Okay? And so my claim here is just that essentially for sufficiently small hardware error rates, you could achieve these criteria. Okay. Now details of like what these numbers are is a TBD calculation, but at least in principle, I believe this works. Okay. So now to turn to the neutral atom implementation. So I think that this platform in particular is kind of very desirable for this quantum memory for a few different reasons. So firstly, the reset operation is very fast compared to sort of active syndrome measurement and feedback. Now, of course, this wouldn't have helped us if the MFQEC circuit was 100 times deeper, right? Then definitely we would lose. But remember that because the Gibbs sampler was local, this MFQEC circuit is finite depth, okay? And in fact, if you're willing to sort of add more and more ancilla qubits into the system, the circuit depth will be at most about 3 times deeper than the circuit depth for one round of syndrome measurement and feedback, okay? And for the neutral atom platform, I think that the price you're paying for this, which is adding more physical qubits, is sort of the price you want to pay, because that's the thing that this platform kind of scales most efficiently at least for the near term. Moreover, these hypergraph product codes that we've been discussing are spatially non-local, but not in a kind of unstructured, kind of pointless way. There's a lot of structure to the non-locality in these hypergraph product codes that's very well suited to the neutral atom array. In particular, if you look at kind of the non-local interactions in these HGP codes, there are interactions between whole rows and columns of bits and checks. And so in this platform, what you're going to do is basically move whole rows and columns of atoms around simultaneously. And so you get kind of square root n worth of these long-range interactions at the same time. Okay? So I think that this is sort of also a very important aspect of this story. And with all of these ingredients in the problem, right, then we, at least in principle, can hope to achieve a kind of autonomous error correction, where we just program our quantum memory with the rules for, move these atoms here at this time, implement reset at this time, and then we can just sort of walk away from the system. We don't look at it, and when we come back, we can retrieve our logical qubits. Okay? That retrieval question may be hard, but at least in principle, they would be there. Okay, so just to kind of recap, here was the punchline of the talk. I sort of went through it before, but hopefully now you sort of agree with me that all of these points make sense. I think in the future, there are sort of two immediate problems that seem worthwhile. The first is basically trying to do this, and I have some ideas about kind of the simplest prototype. And from a more kind of fundamental perspective, going back to the abstract questions, I think that these LDPC codes will teach us a lot about sort of stat-mech and what it means to be in a phase of matter. And I think these may be kind of stress tests for existing intuitions and ideas that we had about thermodynamics and beyond. So yeah, thank you for your attention.
Very interesting talk. Questions?
So yeah, my question sort of has two parts. So the first is how it relates to single shot error correction. Mm-hmm. So it's been conjectured that there's a relationship between single shot, quantum error correction, and self-correction.
Yeah.
But for single shot, every formulation I've seen before really does rely on redundancy. And so, like my first thought is, are your codes not single shot because you've made them non-redundant?
First on that question before I forget, yeah. I believe that the answer is these should be single shot correctable. I think actually one of these papers that I cited does demonstrate this for these hypergraph product codes. So this, I think, is fine. I would almost describe what I'm doing here as, this might be totally wrong, because I wasn't really in this community in 2015 when I think single shot kind of hit the stage. But my understanding is that single shot was maybe kind of, after we couldn't find a quantum memory in 3D, but we did find this other thing in 3D called single shot, then we're just like, okay, this also seems useful, let's just do this instead. I would say maybe you could almost think of this as like a subset of single shot decoders that, if you run this Gibbs sampler for one round, you're if you were kind of too far up in the thermal well, you'll get pushed back down. That's kind of what we want for a single shot decoder. Of course, we introduce our own errors. Maybe that's sort of an annoying thing, but I think that's a sort of silly thing you could fix. But, right, what was I going to say? I think one maybe useful aspect of the Gibbs sampler is that there were certain kind of tricks that we could use, like at least the way we could prove, for example, that these things had very long lifetimes, relied on sort of special facts that you don't know for ordinary single shot. So I think that it's sort of a similar story, but this one is like a subset that maybe has useful mathematical properties. That's kind of, at least at kind of a moral level, how I would think about this. But yeah, to kind of answer the question directly, I think redundancy is not important in that case either.
Okay, because, I mean, that's interesting. The second part of my question was that if these were not single shot, then I would be concerned about how to make this approach fault tolerant in the sense that you'd have to rely on repeated measurements of syndromes, and then when you try to make that memoryless, what's MF stand for again?
Measurement free.
Measurement free. When you try to make something that's not single shot measurement free, that's a problem. Whereas making single shot measurement free is straightforward.
Yeah, so I think what I would say is that, okay, if you're really worried about the fault-tolerant aspects here, you can always choose this circuit in such a way that there's sort of no hook errors introduced into the physical qubits, because you basically, you would sort of arrange things in such a way that in each slice of the circuit, you only sort of measure, let's say, if you're measuring sort of syndromes associated with some cluster of qubits, you're only correcting a single physical qubit. So at worst case, you're only ever introducing, through the sort of decoding process itself, single qubit errors. And so I think that would sort of, and we sort of know already that, right, whatever single qubit error rate we put in, at least if we maybe rescale the correction rate fast enough, that we can always sort of get it below this scale. So that would be the kind of simple argument for why fault tolerance is possible in this setting. Yeah, I mean, I think there's certainly a lot of work to do in terms of optimizing, some of these trade-offs between introducing correlated errors versus simplifying the circuit. So I'm not going to pretend like that's all obvious, but I think at least conceptually, I'm quite confident that fault tolerance is achievable. Yeah.
I have a similar question, which was, in this approach of the measurement free, could you just plug in like this greedy decoder, this greedy local decoder, instead of your like Gibbs weighted one? So it essentially just all.
I think in practice that's what you should do.
Yeah, because it seems like that would be simpler.
It is. Well, I'm a kind of analytic guy, like numeric. Anyway, so the Gibbs sampler was nice because we could do this kind of pen and paper. But I think in practice, indeed, you would just use a greedy decoder. And it seems crazy that the greedy decoder wouldn't be at least as good.
Yeah, I mean, you can also prove things about that one, but it doesn't have the nice feature that it's actually thermal, right? It's like out of equilibrium.
Right, so it's just, the issue was just that for some of the proofs that I was giving, we did need to know what the steady state was. But I think it's more of just a kind of mathematical crutch than a practical one. I would agree with that statement.
I have quite a few questions. I'm going to stick to one. In the argument, when you went to quantum, you were able to still prove that you had this exponential time for the Gibbs sampler, even though the distance was order square root n.
Yes.
And I suppose I'm wondering, do you know what you need in terms of scaling there? Could I do n to the 1/4?
Log n is fine.
Log n is fine.
I mean, basically what you need is
So
just...
something like ha is already, hang on.
Okay, ha doesn't work because, so there's kind of two aspects to the problem. You first need to worry about this factor and then this one. And I don't remember the details, but I think this one is the kind of scary one for Ha's code.
With the linear confinement, you still have linear confinement.
Oh, yeah. You also, yes. Yeah. Dominant's probably right. So this is the sort of crucial feature. Yeah.
Yeah, but then actually you could give up quite a lot of distance and still have this basic behavior.
Yeah, and in fact, like these are kind of the directions I'm thinking in terms of near-term implementations. Like you want something that basically has as little non-locality as possible, but still has this feature. And I think there are kind of tree-like geometries that do this. So.
Okay, in the interest of time, let's thank Andrew one more time.